Section 4.4, Mean Value Theorem for Integrals. Now before we go to the mean value theorem of integrals, I want to review quickly what the mean value theorem for derivatives states. It says that if f is a differentiable function on the closed interval from a to b and continuous on the open interval from a to b, then there exists a c value in that open interval such that the slope of the endpoints, the secant line, is equivalent to the slope of a tangent line at an internal point C. Now, the mean value theorem for integrals states that if f is a continuous function on the closed interval from a to b, then there exists a value of c in that closed interval such that the integral from a to b of f of x dx is equal to f of c times the quantity of b minus a. Now, we know that one of the applications of the integral is that it calculates the area under the curve. What this theorem is stating is that we can also calculate the area under the curve by calculating the area of a rectangle where the height of the rectangle is f of c and the base of the rectangle is b minus a. So what that means as far as the picture is concerned is that if we have a function f of x on the interval from a to b, we can actually take the area that is under the curve of the function and we can calculate a rectangle with the exact same area. Now, here is my value of c, so I make the height of the rectangle at c, and we can see that the rectangle is missing some of the area from the curve in this portion. However, over here on the right-hand side, there are some values that the area of the rectangle includes that the function does not. So this states that we can actually find a rectangle that will have the exact same area as the area under the curve. Let's try an example. Find the values of c guaranteed by the mean value theorem for the function f of x equals cosine of x on the closed interval from negative pi over 3 to positive pi over 3. Now, what the mean value theorem states is that if we integrate from negative pi over 3 to positive pi over 3 of our function cosine of x dx, we will be able to calculate the area under the curve by also calculating the area of a rectangle where the height of the rectangle is found by the function evaluated at c, and the base of the rectangle is the width of the interval. So that would be pi over 3 minus negative pi over 3. To calculate the integral of cosine, we do need to integrate that back to sine of x and evaluate it from negative pi over 3 to positive pi over 3. This is equal to the height of the rectangle, cosine of c, times the width of the rectangle, which is 2 pi over 3. Evaluating sine at the upper limit of integration minus sine at the lower limit of integration is equal to, once again, our area of the rectangle where the base is 2 pi over 3 and the height is cosine of c. If you remember from your pre-calculus days, the sine value at pi over 3 is going to be the square root of 3 over 2. The sine value at negative pi over 3 is negative square root of 3 over 2. Now, square root of 3 over 2 plus square root of 3 over 2 is square root of 3. And what I'm going to do next is solve for the cosine of c by multiplying both sides by the reciprocal of 2 pi over 3. So 3 square roots of 3 over 2 pi is equal to cosine of c. Now, in order for us to actually find the c value, we do need to use inverse trig functions. So we need to take the inverse of cosine. So c is going to be inverse cosine, or arc cosine, of 3 square roots of 3 over 2 pi. Now, when I type that in my calculator, the calculator gives me a value of approximately 0.5971. However, we do need to go back and remind ourselves that the inverse trig functions have restricted ranges. And I can remember from my pre-calculus days that inverse cosine is only going to give me answers between 0 and pi. Now, because our interval goes from negative pi over 3 to positive pi over 3, that means that we will have two answers. One is that 0.5971. We will also have a mirror image of it down here in the fourth quadrant of negative 0.5971. So we actually have both positive and negative 0.5971 as our answers. Now, the height of the rectangle is actually a very important idea in calculus. That height of the rectangle is the average value of the function. So the definition states that if f can be integrated on the closed interval from a to b, then the average value on that interval is going to be 1 over b minus a times the integral from a to b of f of x dx. Now this really is not a different formula from the mean value theorem we saw on the previous page. If I take that mean value theorem, the integral from a to b of f of x dx, which is equal to the area of our rectangle, where f of c is the height of the rectangle, b minus a is the width of the rectangle, and I solve it for f of c, the height of the rectangle. If I solve for f of c, that means I'm going to divide both sides by b minus a. So we end up getting the integral from a to b of f of x dx divided by b minus a. Now, we don't typically write it with the b minus a in the denominator like that. We usually rewrite it as a fraction out in front. So the integral from a to b of f of x divided by b minus a. Now, I want you to think about what you have done in your previous math classes whenever you were asked to find the average. Anytime you were asked to calculate an average, you would add up all the terms and divide by how many. That's actually exactly what this formula says. The integral tells you to add up all of your terms. And then the divide by how many is when we divide by the width of the interval. So even though the formula looks a little bit strange to us, calculating an average is still going to be adding up your values and dividing by how many. Let's try an example of this. Given that f of x is equal to 4 times the quantity of x squared plus 1 divided by x squared, part A, I want you to find the average value of the function on the closed interval from 1 to 3, and part B, find all values of x in that closed interval for which the function equals its average value. So the first thing we have to do is find that average value. Now our formula said that to find the average, which is going to be the height of our rectangle, we take 1 over b minus a, that's the width of the interval, so 3 minus 1, which is 2, times the integral from a to b, so the integral from 1 to 3, of our function. That's 4 times the quantity of x squared plus 1 over x squared dx. Now, before I can actually integrate this, I am going to have to clean this up a little bit. This constant of 4 is a common factor to every term, so I'm going to go ahead and bring that outside of the integral. 4 times the 1/2 that's already out in front reduces to 2. Now, inside the integral still, we have x squared plus 1 over x squared. I do not know how to integrate a quotient, so I'm going to split my fractions up where we have x squared divided by x squared, that's 1, plus 1 over x squared, which is x to the negative second. Next, we integrate. So, integrating 1, that goes back to x, plus, for this one, I'm going to increase the exponent by 1 and divide by the new exponent, and then evaluate from 1 to 3. Rewriting that, we have x minus 1 over x, evaluated from 1 to 3. Then we plug in the top limit of integration, so we'll have 3 minus 1/3, minus plugging in the lower limit of integration. Plugging in the 1, we get 1 minus 1, and that ends up being the value of 16/3. So what that 16/3 represents is the height of the rectangle that we would be able to find that would create the exact same area as the area under this curve. Now, part B is asking us to find when the function equals its average value. So we're going to take the function, which is 4 times the quantity of x squared plus 1 over x squared, and we're going to set it equal to the average value of 16/3, and then solve. Now, in order to solve this, I'm going to cross multiply, and when I cross multiply here, 4 times 3 is 12, and then 12 is going to be distributed into our quantity. So we'll have 12x squared plus 12 equals 16x squared. I'm going to move my quadratic terms over to the right-hand side. So 12 is equal to 4x squared. Divide both sides by 4. We get 3 is equal to x squared. And then take the square root of both sides. So x is equal to plus or minus the square root of 3. Now, if you remember, the interval that we were working on only goes from 1 to 3. So the square root of 3 is the only one that is in that domain. Negative square root of 3 is not in that domain, so I'm not going to list that as an answer. So when the x-coordinate is the square root of 3, we will generate the average value, or the height, of the rectangle of 16 thirds.